Hello, in this video we will talk about the eigenvalues and eigenvectors, but we will start with an example. So, so we suppose that an insect species has the following characteristics. 50% of the 0 years old survive to become 1 year old, and 25% of 1 year olds insects survive to become 2 years old, and no insect goes to 3 years to complete 3 years old. And the last point is each insect can produce an average of 0.25 offspring in its first year, and in the second year they can produce 2 offspring, and in the third year 2.5 per insect. Okay, so this is the data which is given, and we have to we have to model a matrix based on this data. Here is the Leslie matrix. So we will make a matrix which contains all of this information. Okay, so I will label the first column as a 0 years old, number of insects which are present in the first year, from 0 to 1 year. And in the second column I will this is the first one, and this is the second one, and this is the third one. Okay, so in this column I will write the number of insects present in the first year, from 0 to 1. From 0 to 1 years, how many insects are there? I will write them in the first column. And the number of insects which are present from 1 to 2 years old, they will be here. And here I will write the number of insects which are which survive from 2 to 3. Since till the end of 3, all of the insects will get died, so there is no other column. Okay, so look at this. Each insect can produce an average of 0.25 offspring in its first year. So in the first year we have 0.25 offspring, so let's write 0.25, and 2 insects in the second year. So in the second year they produce 2 insects, so here I will write 2, and they produce 2.5 in a third year, so here I will write 2.5. Okay, so this thing I have this information I have put it into the matrix in the first row. In the second row and the third row, you can put this information and this information. Okay, it doesn't matter which row you will put which information, it doesn't matter. So let's put this information into second row. So in the second row you can check 50% means, okay, 50% means 50 by 100. 50 by 100 means 0.5. So 0.5 insects will be, from the total, if total are 1, so 0.5 will reach to 1 year. So in the first year, from this information, we have 0.5 insects in the first year. So I will write 0.5 insects in the first year. Okay. Since this is the only information for the first year, so for the second year and third year I will consider 0, 0, because there is no information given for the second and third year in this row. So here I will write 0 and 0. Then I will put this information in the last row. 25% means 0.25, because 25% can be written as 25 by 100, which is 0.25 if you do it by calculator. Okay, so 0.25 of 1 years will go to 2 years. Okay, so this information says till the second year we will have this 0.25 insects also. Okay, so in this row, in the second year we have 0.25. Since there is no information for the first year and the last year in this statement, so for the first year and the last year I will write 0. So here I'll write 0, here I'll write 0, because they gave the information of the insects which survive till the second year. Okay, so I have written that these are the confirmed number of insects which are present in the second year. Okay, so this is called the Leslie matrix. I will call it L. Okay, since this is the information which says that how many insects will survive if they are present from 1 year to second year, and how many will survive from second to third year, but we don't know from where to start. I mean, if I start from now, that means I don't know how many insects are present. So more information is needed. So the initial information is given. This is called the initial condition or the initial population. So I will write initial population is, so initial population in the first year they were, for example, 50 insects. In the second year, for example, they were 30. In the third year they were 20. Okay, so this is the initial information. So initially you are given the number of insects and you have Leslie matrix, then you can find number of insects in any year. Okay, so these are the number of insects which are given now. So based on this information, based on this Leslie matrix and initial population, you can find the population after any number of years. For example, after 1 year, the population P1 will be L times P0. What does that mean? If you multiply this Leslie matrix with the initial population by just matrix multiplication, I mean put the value of L here and put the value of P0, because both are here. P0 is here and L is here, and then multiply both matrix, you will get P1. P1 will be the matrix contains the number of insects in the first year, means after first year. Okay, and then if you want P2 means after 2 years, it will be L of this, I mean the previous one, the Leslie matrix of the previous one. Okay, Leslie matrix of the population after 1 year, and the population after 1 year is P1. Okay, because if you want to calculate the population after year 2, that means you have to start from year 1, and from year 1 the total number of population was P1. So that means P2 is the population of the insects which are present after year 2. And similarly, if you want to calculate P3, it will be the Leslie matrix of times the population which is present after years 2, which is P2. So I will write here P2. And similarly, I will carry on this process. But the most important thing is that if you put the value of P1 from here, which is L times P0, I can put here L, and this value is L times P0. If I put here L times P0, it will be L square times P0. Okay. Now, if I put here the value of P2, which is again L square times P0, because P2 is equal to L square times P0. If I put this value here, it will be this L as it is, and in place of this P2 I will write L square P0. So I will write L square P0. So I will get L cube P0. Look, when I had P1, that means L to the power 1, P0. For P2, I have L to the power 2. For P3, I have L to the power 3. Similarly, I will carry on. For example, if I write P20, it will be L to the power 20 times P0. Make sense? Just using these facts. Because this fact says P3 equals L3 times P0. This means P20 is equal to L20 times P0. If we do, okay, my aim is not to do these calculations. If I draw these calculations by using any software, P20 will be, the answer of P20 will be 6638 26552 531. And similarly, if I write P21, which is L21 times P0, if I do these calculations using any kind of software, it will be 8297.5 3319 and 663 times 8. If you compare this matrix with this matrix, you will check this matrix is 1.5 times bigger than this. In other words, if you multiply every entry of this matrix by 1.25, sorry, not 1.5, if you multiply each entry of this matrix by number 1.25, you will get this matrix. So I can write this is equal to 1.25 times the previous matrix. Okay, so I will write the previous matrix 1.25 times. Okay. Yeah. So what does that mean? So P21 is 1.25 times P20, okay, because this is P20. So instead of writing this whole matrix, I will write P20 because this matrix is nothing but P20. Similarly, if I do P22, I will get this matrix 10 371.8 41 4.87 and 8 to 9.7. And if you do this calculation, this matrix is again 1.25 times this matrix. In other words, if you multiply each entry of this matrix by 1.25, you will get this matrix, okay? So that means I can write 1.25 times P21. And similarly, I can write P23 is equal to 1.25 times P22 and so on. Okay. In other words, what does that mean? This means the population which was present in the year P20 was increased by a factor 1.25 in the year P21. And similarly, the population which was present in the year 21 was increased by again a factor of 1.25 in the year 22. And similarly, so each times the population gets increased by 125%, okay? Okay, so this means 125% population is increased in the next year, okay? But if you see, the growth factor, which is 1.25, is common in all of the next one, okay? So the growth factor becomes constant after uh, n is equal to 20. After 20 years, the growth factor becomes constant. And this is very good thing. This constant is called the eigenvalue. Okay. So here, the factor 1.25 is called the eigenvalue, and the matrix X which satisfies this thing, Lx is equal to 1.25x, is called the eigenvector. Okay. If you look at this example, you know what is P23? P23 is L times P22, okay? So L times P22, which is equal to 1.25 P22. So L times P22 is equal to 1.25 times P22. Okay, so P22, for example, if this is X, so this is X, so this means L times X is equal to 1.25X. So here our X is P22 in this case. But in this case, our X is P21. In this case, our X is P20. Okay, so again look at the definition. The definition says L times X is equal to 1.25 times X. If in this equation, the matrix X is called the eigenvector. And matrix X is the eigenvector if and only if 1.25 is an eigenvalue.